In this screencast, we'll analyze the stability and oscillatory nature of a second-order differential equation. Provided in the problem statement, we have a differential equation that shows the relationship between a manipulated variable x and a controlled variable y. We know that y at time equals 0 and the derivative of y at time equals 0 are 0. And the question is asking, for what range of k will the system have an oscillatory response, and for what range of k will the system have an overdamped response? The first thing we can look at here is that we have a second-order differential equation. So if we have a second-order differential equation, what that means is the fact that we have a second-order transfer function. With second-order transfer functions, we can analyze stability and oscillations via zeta, where zeta comes from the standard form of a second-order differential equation, which is k over tau squared s squared plus 2 tau zeta s plus 1, where zeta represents the damping coefficient. And the damping coefficient provides some insight into, if a process does oscillate, how quickly the oscillations will subside. So our first step will be to take the Laplace transform of our differential equation and get it into the standard form shown above. So when we do that, the Laplace transform of a second derivative where the y of 0 and y prime of 0 is just s squared multiplied by y. The Laplace transform of the first derivative where y of 0 is just s times y, and the coefficient k maintains. And then the Laplace transform of for y will simply be 4 multiplied by the Laplace variable y, and the Laplace transform of the variable x will just be x. If we factor this out, we can factor the y out of the left-hand side. We end up with y multiplied by s squared plus ks plus 4 equals x, giving us a transfer function of y over x equals 1 over s squared plus ks plus 4. But the important point here is if we look at the denominator of the standard form, we see the fact that the coefficient at the end has to be 1. So in order to modify this, we're going to have to multiply both our numerator and our denominator by 1/4. And when we do this, we end up with our transfer function of y over x equals 1/4 over 1/4 s squared plus 1/4 k times s plus 1. Now that we are in standard form, we can now match our denominator with the standard form denominator. So in other words, what that means is that 1/4 is tau squared, and that 1/4 k is going to be 2 times tau times zeta. So from this, we can determine both tau, and the more important part in terms of determining stability and oscillatory nature of our process here, zeta. So we'll start with tau. We see the fact that tau squared equals 1/4. So we take the square root of both sides. We show the fact that tau equals 1/2. For the sake of our standard form here, it is assume the fact that tau is always a positive value. So to find zeta, we know the fact that 2 tau zeta equals k over 4. If we substitute in the 1/2 for tau, we can easily see the fact that zeta will be k over 4. So now that we have a relationship for zeta, we have to revisit what ranges of zeta lead to what particular responses. And that table is provided here. So from this table of zeta, we can see what values of zeta correspond to either monotonic or oscillatory responses, and what values of zeta correspond to stable or unstable processes. So we can use this table to find the ranges of k for our two parts of the question. So part A asks for when the response will be oscillatory, and we can see from that that will occur in the range shown here. So in other words, the range of when the absolute value of zeta is less than 1. Or in other words, when -1 is less than zeta, which is less than 1. we can substitute zeta in to get -1 is less than k over 4, which is less than 1. And if we multiply everything by 4, we get our acceptable range of k, which is the fact that -4 is less than k, which is less than 4. Part B asks for what range of k will get an overdamped response, and that can be found by looking at our table and seeing that an overdamped response corresponds to a response that is both monotonic and stable. So what we're going to be looking for are values of zeta that are greater than or equal to 1. So again, we substitute in the fact that zeta for our process here is k over 4, and we can determine the fact that our process will be overdamped when k is greater than or equal to 4. So what this shows is that over a particular range of a constant, and it doesn't have to be the one in front of the dy dt term, it could be in front of any of them, it shows that this varying range of k can allow for different types of responses. So therefore, think about it from a control scheme standpoint, is by adjusting the parameters for kc, the controller gain, tau I, the integral time, and tau d, the reset time, we can change the values of these constants in our transfer function, which can change our type of response, making it going from overdamped to underdamped to undamped, or in the opposite order, depending on what value of k is being used.